I didn't see quite significant additional kind of discussion on this kind of topic, but I think I saw a couple of messages about the marks, and typically there are environment kind of changes or differences between students, instructors, and so on. So I think the responses we provided seems to be working sort of for Mac computers. So just follow my message. My message is there if you have not started that, but I think most people have completed this development environment setup. And then there was this information theory basics, which we asked you to sort of read a little bit about the reference. And so with computations could be in Python. So you can use Python for computations. It doesn't have to be marked down to show this, calculate quantities or show whether or not you agree with these equalities. And then the maximum likelihood parameter estimation problem, it kind of follows the Gaussian kind of problem, but with a kind of a sort of a slight different change in this kind of definition of the probability distribution. If you watch the first video, at some point in the video, you will get the log likelihood expression. And what you need to do is you need to obviously is either maximize it, either maximize the log likelihood or minimize the negative log likelihood. And therefore, all you need to do is to calculate the gradient expression. The gradient expression is also shown on this first video. And so if I see something here, you will start your task 1 by producing inter-arrival times. So you have already a lambda. And this is basically the rate parameter of the distribution, which is, I believe, if I remember correctly, it was, it is here 100. And you will produce, let's say, a number of events. You would effectively simulate out of the exponential distribution, and you will be using some library to simulate it. So you don't really expect anything from scratch. You'll use potentially NumPy.random APIs to bring these inter-arrival times in as events. And let's say you generated, 1,000 events. So you have a data generation component from task 1. This is the analogous way of sampling from a Gaussian distribution in the lecture. And then if you have this, since you have now the numbers, the data, what you need to do is you need to implement a stochastic gradient descent that will minimize the negative log likelihood. The negative log likelihood is a minus sign on the expression you will see on video number 1. So you have the expression of the negative log likelihood. And of course, the what you need for stochastic descent is not the expression itself of the negative log likelihood, but its gradient, which is also shown in the same video, with the exception of this minus sign. And so you will have you will follow a kind of a similar approach to implementing 2 for loops. One is going to be an outer for loop that it will go over epochs. So you can define a number of epochs. Epochs is, as you probably heard me in this lecture, a kind of a visitation over the whole 1,000 samples of the data set that someone gave you. If it is 1,000, the number of samples you generated. And then you also have the sort of sample loop now. You go through one sample. You can, of course, implement stochastic gradient descent with just one sample. You don't have to have a mini batch of greater than 1. It works with 1. And you will, so inside this kind of for loop, you will randomly select the sample from the population. You will plug in the sample into the gradient expression, because if you see the gradient expression, obviously has some dependency on the sample and also on the lambda parameter. And you will then have the stochastic gradient descent equation, the parameter update equation, which requires a learning rate, which you need to tell us, what it is, obviously, in the code. And you will, obviously need to implement another line, which is the loss function itself, the negative log likelihood function itself, because we would like also to see it as a plot. So at the end of these two for loops, you will do two things. One, to print out the final lambda after all these epochs and iterations are done. The second for loop, the inner for loop are done, and you will plot the sort of the loss, the negative log likelihood over. I think we are asking you over the iteration number, which is a combination of the epoch and the samples that each epoch contains. Okay, so that's basically I think the second exercise you shouldn't have really any problem, and I think from some tickets that I have seen, people are in kind of a good trajectory there. And then the third final kind of problem is very analogous to the problem that you've seen in the textbook, the Python textbook. In fact, it's fairly straightforward to do the extension. You effectively take the code and you from the textbook and you augment it with the changes. What are those changes? Well, evidently, over here we have a data set which is a sinusoidal in nature, so you can see exactly how the sinusoidal data set gets generated in the website. And then you need to change the loss function. Okay, and because you are changing the loss function, all you need to do is to calculate the gradient of the new loss function, which involves now a regularization term. And this is the only line that you need to change in the code, because this thing should converge to the m is equal to 3 model, if you like. It should converge to producing a W star vector that, because of this regularization, only the first few terms are effectively non-zero, and the remaining terms are potentially very close to zero. Okay, and this is in order to show that and get the full points. Obviously, you need to show the impact of regularization. So even if you expanding significantly larger than 3 hypotheses, in this case 9, for example, then only the first 3-4 terms of that W star vector are non-zero, and the 5, 6, 7, 8, and 9 are close to zero at the end of this stochastic gradient descent algorithm, pointing to the hypothesis, which looks like more or less sinusoidal as well. So this code for that one you will find in your chapter 4 of your Python, on your Python textbook. Okay. Any questions?
That was very helpful, Professor. Thank you.
Okay, no problem.
So just to confirm, right? I mean, on the submission, if no one has any question, so
Yeah.
we are submitting the notebook in both Brightspace and also like when we open the project, right? When we open your repository, the course repository in the container. So we are actually submitting the notebook in both the places, and then we are also committing our changes to our repository in GitHub, correct?
So there is a web page where you can, on the course site, I think I referred to it, that how to submit it. So the first job that you need to do, and there is a video. Inside that video, first of all, they ask you to edit this line 34, where the GitHub ID of your collaborators are. Obviously, your collaborators are the TA, is the TA of this course. There's only one TA in this course. So you basically take the GitHub ID, his GitHub ID, and you put it here, deleting all the remaining GitHub IDs quoted in this list. Okay, this is for your workflow when you commit your changes. for the workflow to be executed and check that the TA has access to it, and you get a green check mark at the repository kind of action view in GitHub. This is my repository. Evidently, it is sitting in GitHub. Let me just go quickly to that location. Okay, sorry, what is the version control? So here is your remotes, and this is where I am. Oh, what happened? Okay, here it is, right? So you have the option to when you sign in, you have the option to, you will see a plus icon over here, and by clicking this plus icon, you are able to make the repository your own. It's a process called import. The other process is to clone it and then change the remote manually. Okay. So at the end of the day, you have the repository. It's very important for your own repository, which is a clone of this thing, potentially, to be your own. Okay, and be your own, obviously, and be private. So we ask you to make all the repositories private, and also we ask you to insert a collaborator. So when the action is executed, the collaborators are checked and everything is fine. You will place, let's assume that you do the development environment in a Docker container. Obviously, you have some notebook there. If you work with a Docker container from within the repository, the notebook is likely already under the assignment somewhere. It's probably under the assignment 1. This notebook is a dummy notebook. If you open it, you will create an error because it just doesn't have any bytes inside. It's just a placeholder. So if this is your notebook, please save the output of the notebook. And so the collaborator, the TA, is able to just click on it. GitHub will parse it and will see the result and will grade appropriately and give you your grade in Brightspace. If you don't, and you do the implementation outside of a Docker container inside a collab, for example, environment or some other environment, you have to copy the notebook. You have to download it from collab and copy it over into your GitHub repository. And also make sure that the outputs are saved. So again, the TA will just open the notebook and will just grade without really doing much. So so bottom line is that what you submit is you submit this URL. Okay, you submit this URL to Brightspace and on Sunday, preferably at 11:59 p.m. before 11:59 p.m. and then you will you'll be fine. So Brightspace only accepts URLs, and there's only one URL you submit in each assignment. Because the TA knows that you're submitting an assignment at this specific deadline, it will go to assignment 1 or 2 or 3, whatever folder it is there, and it will grade it.
Can we do this all, or at least for this assignment, in one single like IPYNB file that has the Python and the markdown all at once?
Oh, yes, I mean, yeah. Assignment 1 could potentially be just one notebook, right? And this notebook will contain a mixture of Python and markdown, obviously. You are, of course, free to break the assignment into multiple parts and multiple notebooks, that is, and put it under the assignment 1 folder. Yeah.